Actually, this session is the very last one of the Earth Science track, and also the final hands-on session of this ACM school. So thank you very much for staying with us until the end of this intensive program. Actually, after this session, it's time for lunch. So we will aim to keep things smooth and on schedule. Okay. My name is Seiya Nishizawa. I am a researcher at RIKEN, and I am one of the core developer of the scale atmospheric modeling framework. And I am joined today by two tutors from scale development team. One is Dr. Adachi, there, and Dr. Kawai, there. And we will be walking around during the tutorial, so please feel free to ask anytime. So just before this session, you attended Dr. Kajikawa's lecture on high-resolution climate modeling and diagnostic studies. This hands-on intended bridge from those concepts to the practical workflow of running the atmospheric simulation model on an HPC system. Today, you will actually build and learn the scale regional model on Fugaku and see how such simulations are carried out in such supercomputers. Okay. I will start with two short videos introducing the scale. After that, I will briefly explain about the tutorial tasks and important documents we will use. After that, we will move into the hands-on work on Fugaku. The first video, it provides a general overview of the scale framework and was generated using an AI tool, the Google Notebook LM. Most of you may know well. And the second video introduced the cutting-edge cloud microphysics scheme named Super Droplet Method, SDM for short, implemented in scale. Please enjoy these short introduction before we begin the practical part. Okay, I'm starting the first video, the overview.
Hello, everyone, and a very warm welcome to the ACM's second ASEAN school. Have you ever wondered how we predict something as huge and powerful as a typhoon? Well, it takes more than just satellites. It takes some of the most powerful computers in the world. Today, we're going to look inside one of these incredible tools, a weather model called Scale-RM. So here's a quick look at our plan. We'll start with why we even need supercomputers for weather. Then I'll introduce you to the scale framework itself. We'll look at what makes it so fast and powerful, and some of the cool science it can do. After that, we'll talk about your mission for the hands-on part of the tutorial, and then we'll be ready to get started. Okay, let's jump right in. Section 1, why do we need supercomputers for the weather? It all comes down to the challenge of prediction. So, how do we actually predict the weather? I mean, we all look at the forecast on our phones, right? But what's happening behind the scenes? Well, scientists have to figure out a way to understand the chaotic dance of the atmosphere. And the way they do it is really amazing. They build a digital version of the sky. And that digital version of the sky has a name, a regional weather model. The best way to imagine it is like a digital twin of the atmosphere for a specific part of the world. It's basically a giant computer program that follows all the rules of physics. You know, how the air moves, how clouds are born, how the sun heats up the land and sea. It tries to copy everything, which, as you can guess, is a huge amount of work for a computer. So to make this digital twin work, what we do is we divide the atmosphere up into millions and millions of tiny little boxes. Think of it like a giant 3D grid. And for every single one of those boxes, the computer has to solve some really complex math equations over and over again for each step in time. This is what makes the weather model run. And solving all of that for millions of points, well, it's an absolutely huge job. That's exactly why predicting the weather is one of the classic big challenges for high-performance computing. So how do we actually handle a problem this big? Well, that brings us to our main tool for this tutorial, the scale framework. And there it is. The name, SCALE, stands for Scalable Computing for Advanced Library and Environment. It's a really modern and powerful system for simulating weather and climate, and it was developed right here in Japan at the famous RIKEN Center for Computational Science. Now, this is a really important point about scale. It isn't just one big single model. It's actually better to think of it as a library, or maybe even like a box of Lego bricks for scientists. It gives them all these powerful, ready-made pieces that they can put together in different ways to build their own custom experiments. This building block approach is what makes scale so flexible. And you can see that structure here. It's like a stack. At the very bottom, you've got the hardware, the supercomputers, the GPUs. Then you have the system software that makes it all work. Things like MPI and NetCDF. On top of that sits the main scale library. That's our box of Lego bricks. And then right at the top, you have the actual models that scientists create, like Scale RM, which is the one we're going to use.
Okay, now for the part I think you'll find really interesting, especially with your background in HPC. Let's talk about what makes Scale so good at running on big computers.
All right, before we talk about Scale's performance, let's just quickly review two really important ideas in supercomputing: weak scaling and strong scaling. So weak scaling asks the question, if I get more processors, can I solve a bigger problem? It's all about going larger. Strong scaling, on the other hand, asks, if I use more processors on the same problem, can I solve it faster? That's all about speed. And of course, a truly great piece of software needs to be good at both. And this is where Scale really shines. It was designed from the very beginning to run on these huge, massively parallel computers. It has excellent weak and strong scaling. It's also been optimized to run really well on modern GPUs using things like CUDA. And one of the best things, I think, is that it's completely open source. That means anyone in the world can use it, check the code, and even help make it better. So, okay, we've got all this amazing computing power. But what does it let us do? Let's look at the advanced science that's possible because of it. This is really about building a testbed for the future of weather science. One of the most exciting things inside Scale is something called the super droplet method, or SDM for short. You see, most older models have to simplify how they handle clouds. They just look at the average conditions. But SDM is different. It's a particle-based model. It actually tracks thousands of individual little packets of water droplets, these super droplets. This gives us a much more realistic, much more detailed picture of what's really going on inside a cloud. So you see, Scale is much more than just a tool for making tomorrow's weather forecast. It's really a platform for innovation, a kind of sandbox for scientists. It's a place where they can try out new ideas, test new physics, and even implement next-generation methods. Because it's designed to be easy to modify, it really encourages scientists to experiment. All right, that brings us to the most important part of today, your mission. Let's talk about what you're actually going to do in the hands-on session. So what are we going to do? Well, you're not just going to type in commands that we give you. For this tutorial, you are going to be the scientist. You're going to run a real experiment. And the process is pretty straightforward. First, you'll follow the guide to set up a realistic weather experiment. Second, you'll run the Scale RM model. Then, and this is the fun part, you are going to go into the configuration file and change one of the settings yourself. And finally, you'll run the simulation again to see what effect your change had on the result. It's a simple 4-step process. And that's it for the introduction. Hopefully, you now have a good idea of the tool we're using and what you're going to do with it. So, let's get started.
Okay, now we are moving to the next video, introducing the SDM.
This shows the entire life cycle of a cumulonimbus cloud simulated by a state-of-the-art technique known as the super droplet method. First, about the super droplet method. This is a cross-section view of a cumulonimbus cloud. At close range, we see that the upper region contains ice particles of various shapes. while the lower region is filled with a vast number of water droplets. In between, there's a complex intermingling of ice particles and water droplets. In the superdroplet method, water droplets similar in nature are grouped together and represented as a single unit, called a superdroplet. While the ice particles are represented in a similar manner, their shapes vary considerably, so they're modeled as spheroids with holes. Unlike previous methods, this one calculates cloud behavior from the particle level, reproducing the particle motions, formations, growth, and interactions within the cloud. These visualizations show the entire life cycle of a cumulonimbus cloud, simulated with high accuracy using the new superdroplet method.
Okay, now let's move into the tutorial part. So in this tutorial, you will prepare the environment and build scale regional model on Fugaku, and run the standard real atmospheric experiment with prepared configuration, and then try an advanced experiment by modifying the domain location and the simulation period. For the advanced cases, you can choose the events within August 2009 or November 2025, which include a strong typhoon in Southeast Asia. All necessary code and input data have already been prepared on Fugaku. So you can focus on understanding the workflow rather than the data preparation. So you will use the two main documents throughout the session: the tutorial slides and the scale user's guide. These slides, the slides provide a high-level explanation overview and point you to the relevant sections of the user's guide, which contains a detailed explanation. You can download from the Google Drive to document. So if you do not have them yet, so please download first in the practical part. So you participants have diverse backgrounds. Some of you have used the scale or WRF before, but others are new to atmospheric modeling. So we will not proceed in strictly synchronized way. Please follow the instructions at your own pace, and raise your hand whenever you need help, support. Okay, with that, let's begin. Please open the tutorial slides, log into the Fugaku, and start with the preparation step. And there's no need to rush. We, the tutor, are here for help. So you can please download the tutorial slides, and probably you can find them from here, hands-on materials. You can download two documents, slides and the user's guide. And this slides provides you instruction step by step. Okay, let's get started for the hands-on tutorial. Please download and work the instructions. And if you need help, just please raise your hand. Okay,